Hello everyone, my name is Johar Rafid and welcome to my presentation on machine learning in database management system. Over the next 10 minutes, I will walk you through why this topic matters, what researchers and cloud vendors are actually building in the industry, and how the industry is adopting it, and what are the challenges and risks of machine learning in DBMS. So let's get started. So let's get to the background first. Database management system have powered software for over 50 years using hand-tuned heuristics like B trees for indexes, histograms for guessing how many rows a query will return, and dynamic programming for choosing how to run a query. These ideas are brilliant, but they were designed for a world of small, predictable databases. That's not the world we are currently living in. We are actually dealing with petabytes of data, big data, real time data analytics. A modern DBMS system exposes hundreds of tunable knobs per database management system, and a simple complex analytical query can have billions of valid execution plans. So the central question of my presentation is, can machine learning replace or augment the hand-tuned components inside a database, and can the database itself host the machine learning model? So machine learning and database, it's basically a two-way relationship. There are actually three threats that works here. For the first is machine learning is inside the database management system, where machine learning replaces the heuristics with learned models, indexes, queries, optimizers, knob tuning, and physical design. The second is for the database management system for the machine learning, where running machine learning models directly on top of the database using SQL query, so we don't have to export our data to Python or separate machine learning models. And the final part is where we uh, combine both of these concepts, where the database itself tunes, indexes itself, partitions itself, and even repairs itself without any sort of human intervention. My report covers all three, but we are mostly focused on the first part, which is machine learning for database management system. So where is the classical playbook breaks? Let's look at exactly how the modern classical database management system used to be. The AB trees and the B plus trees, they're all brilliant, but it's data oblivious. It gives the same lookup time whether your keys are random or perfectly predictable. So if your data has a pattern, a B tree is doing wasted work. Histograms with independence assumption, that's how cardinality estimation has been done for decades. But Lace and his colleagues showed in 2015 that the estimates can be wildly wrong on multi-table joins, and the errors compound, leading optimizers to confidently pick disastrous plans. And manual database tuning has simply hit a scale wall. Hundreds of knobs times thousands of databases plus shifting workloads is actually infeasible. No human team can keep up with this amount of workload. That's where machine learning gives us an opportunity. Learn from the data itself, adapt to each workload, and automate at a cloud scale. So first, the Kraska at 2018 gave us the opportunity of learned indexes. There are three approaches in this literature. The first is to learn the cardinality My first key finding is learned indexes, the idea that started this whole field. In 2018, Tim Kraska and colleagues at MIT and Google made a really elegant observation. An index is just a function that maps a key to a position. So if your keys are predictable, why not just learn that function directly using machine learning? Their proposal, the recursive model index, or popularly known as RMI, uses a small hierarchy of models to predict where a key lives, then does a tiny last mile search to correct any error. The result is fewer comparisons, less memory, and faster lookups on read heavy workloads. They reported up to 70% faster than a cache optimized B tree. There are other follow up systems like PGM Index, Alex, and Fitting Tree, which also enabled us the learned indexes. But there's a catch. That this is honest critical analysis. Industry has been cautious here. Learned indexes shine on read heavy analytics, but under high write rates, retraining becomes expensive, and tall latency guarantees are hard to maintain. So this is my first finding. My second finding is learned query optimization, and it's probably the most ambitious target inside our database management system. There are three approaches in the literature we are going to explore. The first is to learn the cardinality estimator itself. Systems like MSCN and DeepDB uses neural networks or probabilistic models to predict how many rows a query will return, and they handle the correlated columns far better than the histograms. The second is bolder. Learn the plan selection policy directly. Neo from Marcus and colleagues in 2019 uses RL, popularly known as the reinforcement learning. It picks join orders, runs them, and observes how fast they were, and updates its policy. Over time, it can outperform a hand tuned optimizer, but it's risky in production because a bad early decision can take down a service. That brings us to the hybrid approach, and this is the most important takeaways from my report. BOW, also by the Marcus Group in 2021, does not replace the optimizer. It keeps the existing post GRE planner and only learns which hints to apply. Machine learning guides classical decides. This pattern preserves the predictability that production systems need, and it's now the dominant industrial design. The third and finding, which is machine learning has been doing the best, is tuning. Machine learning driven self tuning has had real practical success. AutoTune from Carnegie Mellon uses Gaussian processes to recommend values for hundreds of database knobs. Alibaba's CDB Tunes uses deep reinforcement learning to do the same at a very large scale. Both outperform default settings and dramatically reduce the database administration effort. In database, machine learning flips the relationship. Instead of using machine learning to make the database faster, it lets analysts train and apply machine learning models with SQL using statements like create model and ML predict, Snowflake Cortex, and SQL Server. Machine learning services have made this mainstream. The benefit is huge. You don't move terabytes of data to Python, you bring compute to the data, and governance stays in place. And there's self-serving databases. This is the future we are looking at, where every concept combines a database management system that observes, predicts, and acts on its own workload, where there will be full autonomy and no human will be involved. So in this large scale model, and there must be a lot of opportunities. At the same time, there will be limitations, challenges, and risks. The first opportunity is the adaptability. There will be an automation at scale because it's a large scale project, so there will be a lots of automations. It unlocks new functionality like workload predictions and anomaly detection, natural language to SQL, and smart recommendations, and there will be less data movement, which is the dominant bottleneck in modern analytics. With all these opportunities, there will be a lots of limitations too. Workload drift means a model trained on yesterday's queries may fail badly on tomorrow's. Neural models give no worst case guarantees. They can be arbitrarily wrong on out of distribution. Learned components are hard to debug because the bug could be in the data, the training procedure, the architecture, or the deployment, and there are genuine privacy concerns too. So what will be the future research in this field? So of course, as I said earlier, the future should research, or the future goal is the autonomous database management system where no human involvement is needed. For that, lifelong learning is very important. Almost all published evaluations train and test on similar query distributions. Almost nobody studies what happens after months of production drift. Second is robustness and verification. There is benchmarks and reproducibility. Many high profile results have not been independently reproduced. OLTP oriented benchmarks for learned components are scarce. There should be clear guidelines of privacy, security, and fairness. So, this is how I will conclude. First, the gains are real. There are three takeaways to uh, actually conclude this presentation. The gains are real, but the scope is narrow. Machine learning works best so far on read heavy analytics, configuration tuning, and physical design recommendations. Second, machine learning guides classical decides. The hybrids are winning. And third, trust is the bottleneck. Robustness, lifelong learning, fairness, and privacy must mature before fully autonomous database management systems are trustworthy. Thank you for listening. So, goodbye.